Hello everyone. In this class we will see the next test, that is D-Alembart's ratio test. In the last class we have seen about Cauchy's root test, how we have to check the nature of the given series by Cauchy's root test. Today we will see about D-Alembart's ratio test. First, let us see the statement. If summation un is a series of positive terms, we know that this summation un indicates what? Sum of the first n terms. Un indicates the nth term of the series and the summation indicates sum of the first n terms. If that series is of the positive terms, then if limit n tends to infinity, un plus 1 means the term un plus 1th term divided by un means nth term is equal to L. If this term gives a finite quantity, here this L must be what? A finite quantity. If this term, that is limit n tends to infinity, un plus 1 divided by n is equal to L, where L is a finite quantity, then summation un is convergent if L is less than 1. If this finite quantity is less than 1, we say that the given series is convergent, and divergent if L is greater than 1, and the test fails if L is equal to 1. Here for convergent, divergent and for test fails condition are same for D-Alembart's ratio test and also Cauchy's root test. Here only the statements are changed. In Cauchy's root test, to find the nature of the series, we have to find limit n tends to infinity un raised to 1 by n. Here in D-Alembart's ratio test, we have to find limit n tends to infinity un plus 1 divided by n. If this limiting value is equal to a finite quantity, if that finite quantity is less than 1, we say that the given series is convergent, and if that value is greater than 1, then we say that the series is divergent, and if L is equal to 1, then we say that for the given example, this test means D-Alembart's ratio test fails for that given example. Okay, now let us see the examples. First example, test for convergence of the series 1 square by 2 plus 2 square by 2 square plus 3 square by 2 raised to 3 plus 4 square divided by 2 raised to 4 plus and so on. We have to check whether this series is convergence or divergence by using D-Alembart's ratio test. Okay, now our first thing is what? First we have to identify what will be the nth term of this given series. To identify that, first we have to clearly observe what are the terms, beginning terms given in the series. On observing that, we have to write the nth term or the general term for this given series. See, numerator terms are 1 square, 2 square, 3 square, 4 square. Okay, and denominator terms are 2, 2 square, 2 cube, 2 raised to 4. Now, see, the base terms are changing here, and here in denominator, power, here nothing is there means this 2 has a power 1. Here power values are changing. If you consider these changing values are n, means when you consider these changing values are n, then we get un, nth term is n square divided by, here 2, base term is constant, here power are constant, 2 raised to n. While we are assuming this changing terms as n or anything, first check whether that assumption is satisfied for all the terms or not. We are not taking here randomly n square and 2 raised to n. Before taking this one, we have to cross check whether this condition or our assumption satisfy all the terms of this series or not. See here, substitute 1, what we will get? 1 square divided by 2 raised to 1, same as the first term, and we consider n as a 2, it will be 2 square divided by 2 raised to 2, means 2 square. When n is equal to 1, substitute u1. What is mean by u1? u1 is the first term, it satisfies 1 square divided by 2, and we substitute second term, u2 is equal to 2 square divided by 2 square, plus when we substitute it as a 3, it will be 3 square divided by 2 cube, and when we substitute n as a 4, u fourth term is equal to n square divided 4 square divided by 2 raised to 4. See, this our general term or the nth term satisfies this given 4 terms. Means what? Our assumption is right here. We are taking nth value as n square by 2 raised to n is correct. Our un value means nth term of this given series is what? N square divided by 2 raised to n. And now we shall apply D-Alembart's ratio test. We know that D-Alembart's ratio test is limit n tends to infinity un plus 1 divided by un, right, which is equal to, here limit n tends to infinity, here this is a un term, means nth term, here we want un plus 1th term, means wherever n is there you have to just replace by n plus 1. If you are confusing in substituting the values, better you will find first what is un plus 1, after that substitute here. Here I am directly substituting un plus 1th term, it will be n plus 1 whole square divided by 2 raised to n plus 1. Now the denominator term, when we write it as a whole divided by this one, it will be what? N square divided by 2 raised to n in this denominator. In place of that I will write here as, when we take this in multiple, it will be what? 2 raised to n divided by n square. I think you know this one. Okay, now which is equal to limit. Before applying the limit, first you have to simplify these two terms, n plus 1 whole square into 2 raised to n divided by, see this 2 raised to n can be written as 2 raised to n plus 1 can be written as 2 raised to n into 2, because here we have bases are same. When we add the powers again you will get what? 2 raised to n plus 1, therefore it is 2 raised to n into 2 into n square. Then this 2 raised to n cancel with this numerator 2 raised to n. It will be here 1 by 2 is constant. You may take this constant outside the limit. Limit 1 by 2 into limit n tends to infinity. The remaining is n plus 1 whole square divided by n square. See, now our duty is what? We have to apply the limit. But before applying the limit, just see what we will get after applying the limit. See, when we substitute n as a t, n as a infinity, infinity plus 1 is again a infinity, infinity square is again a infinity. It will be what? Infinity square divided by infinity square means it will be, we get infinity by infinity term, right? Infinity by infinity term means we get infinite value after applying the limit here. So that first we have to see what we will do to avoid this infinite quantity, because we know that according to our D-Alembart ratio test, that limiting value should be a finite value. It may be less than 1, greater than 1, or equal to 1. But it may be what? A finite value, not a infinite value. So that here try to change this term. Here I have a limit n tends 1 by 2 into limit n tends to infinity. See, in this term I will take n square common. When we take n square common, it will be what? N square get cancelled. For that, we will not get a infinite value here. I will take n square common. It will be what? Since we have a square, so I will take n square here. 1 plus 1 divided by n. Okay, in this two term I am taking n, since it is a n square, so it will be n square common. 1 plus 1 by n whole square divided by n square. This n square cancel with this one. We have 1 by 2 into limit n tends to infinity 1 plus 1 by n whole square. 1 plus 1 by n whole square. Now we will apply the limit here. We know that 1 by infinity is 0. As I say in earlier classes, 1 by infinity value is what? 0. 1 plus 0 is again a 0. 1 plus 0 is again 1. 1 by 2 into 1 plus 0 whole square. 1 plus 0 whole square is 1. 1 square is again 1, which is equal to 1 by 2. 1 into 1 by 2 is again a 1 by 2. See, this 1 by 2 is what? Less than 1. Limit n tends to infinity un plus 1 divided by un is equal to 1 by 2, which is less than 1. We know that if our limiting value is less than 1, then according to D-Alembart's ratio test, this given series is convergent. We will write the conclusion here. Thus, by ratio test, summation un is convergent. Summation un is convergent. This is how you have to solve the examples by using D-Alembart's ratio test. If you want, first calculate un plus 1. After that, substitute that value in this limit n tends to infinity un plus 1 divided by un term. Next example. Second example. Test for convergence of the series 3 divided by 4 plus 1 plus 3 square divided by 4 square plus 1, 3 cube divided by 4 cube plus 1, 3 raised to 4 divided by 4 raised to 4 plus 1 plus and so on. This is as similar as the previous one. Just you have to identify what will be our nth term for this given series. See here base values are same in the numerator, only the power values are changing, and here also the base values are same. Here power values are changing, so that the changing values as considered as n for nth term, so that our un term will be what? Then we may write it as by data un term is nth term is un is equal to 3 raised to n divided by 4 raised to n plus 1. Un term is 3 raised to n divided by 4 raised to n plus 1. Before going to the result of D-Alembart's ratio test, we know that in that result we have un plus 1. For your convenience, first calculate what will be the un plus 1th term. Otherwise you will go to direct result. After that find what will be the un plus 1. Otherwise first calculate un plus 1. Therefore un plus 1 term is 3 raised to n plus 1 divided by 4 raised to n plus 1 plus 1. These two are in the power. Okay, this is plus 1, this plus 1 is here. Now by D-Alembart's ratio test, by ratio test or D-Alembart's ratio test, limit n tends to infinity un plus 1 divided by un is equal to un plus 1 is 3 raised to n plus 1 divided by 4 raised to n plus 1. Do not write un plus 1 again in a denominator for your easier calculation. Into write it as a 4 raised to n plus 1 divided by 3 raised to n. It will be. Next is, which is equal to this 3 raised to n plus 1 can be written as 3 raised to n into 3. 3 raised to n into 3 divided by 4 raised to n plus 1 plus 1. Sorry, I have forgotten to write limit here. Limit n tends to infinity. This one here also equal to limit n tends to infinity is there, plus 1 into 4 raised to n plus 1 divided by 3 raised to n. This 3 raised to n cancel with this 1. If you want, take this 3 which is a constant outside the limit. Otherwise you can write here only. Since this is a constant, I will take outside the limit 3 into limit n tends to infinity. This is equality. 3 into limit n tends to infinity. The remaining terms are, here 3 I am taking outside the limit, 4 raised to n plus 1 divided by 4 raised to n plus 1 plus 1. This is our remaining term. Here also, before applying the limit, just see what we will get after applying the limit. We know that anything raised to infinity is again a infinity. Infinity plus is again a infinity. So that after applying this limit, we will get an infinite value. To avoid that one, what we will do is 3 into limit. Try to avoid means try to cancel the terms having the possibility to give an infinite value. Here in numerator I will take 4 raised to n as a common. Here remaining is 1 plus 1 divided by 4 raised to n whole divided by. Here in denominator I will take 4 raised to n plus 1 common. The remaining is 1 plus 1 divided by 4 raised to n plus 1, which is equal to 3 into, we know that this 4 raised to n plus 1 can be written as 4 raised to n plus 4 raised to n into 4. That 4 raised to n cancel with another 4 raised to n. This concept is same as this one. See somewhere, this one. 3 raised to n plus 1 as written as 3 raised to n into 3. 3 raised to n cancel with this 3 raised to n. Remaining is 3 here. Here also same, we get only 4 in the denominator. It will be 1 plus 1 by 4 raised to n divided by 4 is remaining 1 plus 1 divided by 4 raised to n plus 1. Okay, now 1 by 4 is also a constant value, so that you have to take outside the limit 3 divided by 4 into limit n tends to infinity 1 plus 4 divided by 1 plus 1 divided by 4 raised to n divided by 1 plus 1 divided by 4 raised to n plus 1. Now apply the limits. When we apply 4 raised to infinity, it will be infinity. We know that 1 by infinity again a 0. then 1 plus 1 divided by 4 raised to n plus 1. Here when we apply infinity, it will be infinity. 1 by infinity as again a 0. 1 plus 0 is 1. 1 plus 0 is 1. 1 divided by 1 is 1. 3 divided by 4, it will be into 1 divided by 1, because this value is 0, this value is 0. 1 by infinity is 0, 1 by infinity is 0, which is equal to 3 divided by 4. Limit n tends to infinity, un plus 1 divided by un is equal to 3 divided by 4. We know that 3 divided by 4 gives a value which is less than 1. When we calculate this one, we get a value which is less than 1. We know that by D-Alembart's ratio test, if this limiting value gives a finite value which is less than 1, then our given series is convergent. We have to write the conclusion. Thus, by ratio test, summation un is convergent. Summation un is convergent. Third example, discuss the nature of series x divided by 1 into 2 plus x square divided by 2 3 plus x cube divided by 3 into 4 plus and so on, where x value is greater than 0. Here also first we have to identify the nth term of this given series. Let un is equal to, here x is as it is, here power changing, take this as a n, divided by, see here first value is 1. Here we are taking values of n from 1, right? So that this value for this term, n value is 1, it will be what? If n is equal to 1 for this term, okay, here I am considering the powers values are as n, means when we consider n as a 1 for the first term, we will get what? u1 term, that is x raised to 1, and that n must be satisfied for the numerators also. Here we have how to take the denominator term for un. Here n value is 1 for first term. Since this is a first term, value of n is 1. This is it will be satisfied for this x, means numerator term. Now we will take the denominator term. Here n value for this first term, n value is 1, means this is n, correct? N is equal to 1 means this is n. Now into 2, here n is 1 means when here we have 2 means n plus 1, n plus 1. See, as I say in earlier example, while you are taking the value of, means the term un, just you have to cross verify whether this un term satisfy for all the given beginning values of this given series. See, when you take n as a 1, you will get a first term, that is u1. See, n is equal to 1, it will be x divided by 1 into 2. When it is second term, n is u2, x square divided by 2 into 3. N is 2, 2 plus 1 is 3. Therefore, this our un is satisfied for given beginning values for the series. So that our un is correct for this given series. Now, therefore, if un is equal to x raised to n divided by un plus 1, then what will be our un plus 1 is equal to x raised to n plus 1 divided by n plus 1 into, in place of n plus 1 we have to take n plus 1, this is n plus 1 plus 1, which is equal to x raised to n plus 1 divided by n plus 1 into, solve this one, n plus 1 is 2, n plus 2. un plus 1 term is x raised to n plus 1 divided by n plus 1 into n plus 2, and un term is x raised to n divided by n into n plus 1. Now, by ratio test we get what? limit n tends to infinity un plus 1 divided by un is equal to un plus 1 term is x raised to n plus 1 divided by n plus 1 into n plus 2 into this is n into n plus 1 divided by x raised to n. Next, see here this n plus 1 term cancel with this n plus 1 term, and this x here also I have forgotten to write limit here, sorry for that. But if you forgot to write limit n tends to infinity in examination, definitely you will lose the marks. So please careful while you are writing these terms. Limit n tends to infinity x raised to n into x, this can be written as x raised to n into x into n whole divided by, here n plus 1 cancel with this n plus 1, remaining is n plus 2 into x raised to n. This x raised to n cancel with this one. We have the terms limit n tends to infinity x into n divided by n plus 2. See here we are applying limit for n, not x. Therefore this in this term x is considered as a constant. If you want, take this x outside the limit, otherwise keep as it is, as you wish. Both will give the same answer. Then here also we get a infinite value when we apply this limiting value as n tends to infinity, so that we will consider this limit n tends to infinity xn divided by n plus 1 as limit n tends to infinity x into n divided by, here I will take n as common, 1 plus 2 divided by n. Then this n cancel with this one. Remaining is here n, x is a constant. Limit n tends to infinity 1 plus 2 divided by n. We know that anything divided by infinity is 0. 1 plus 0 is again 1. 1 into x is x only. This is x into 1 means this is x. Therefore we have limit n tends to infinity un plus 1 divided by un is equal to x. Here they are given x is greater than 0, right? X is greater than 0, but we don't know this is either less than 1, greater than 1 or equal to 1. So that for this example our conclusion will be what? We have to write like this. Thus by D-Alembart's ratio test, D-Alembart's ratio test, summation un is convergent if x is less than 1, divergent if x is greater than 1, and we have another condition, and the test fails if x is equal to 1. If you have a limiting value as unknown, you don't know definite value for this limiting function, limiting value, you have to write the conclusion like this. Here x is unknown. Simply they are given as x is greater than 0, but we don't know whether that x is less than 1, greater than 1 or equal to 1. So that our conclusion will be what? By D-Alembart's ratio test, summation un is convergent if x is less than 1, divergent if x is greater than 1, and the test fails if x is equal to 1. Conclusion will be like this. We will see some more examples in the next class. Here you have to understand how to take nth term of the given series, and careful when you are solving this un plus 1 divided by un, and practice yourself to avoid the terms which gives the infinite value for this limiting values. Okay, write down the notes and practice all these 3 examples. If you have any doubt, we will see in live classes. Okay.